Hello. Good morning.
Morning. Good morning.
It's just brutal.
Good mid-afternoon.
Okay, let's jump back in. Let's review real quickly what we were doing last time. So let me give a little feedback. So last week's, not last week, but last Monday, last session's lecture on complex numbers, how many of you would say that material was already familiar to you? How many would you say that was more or less completely new?
Yeah, it's been like 6
Yeah.
years.
So that was, okay. Did you track with it? Did
More or less.
more or less? Okay, what was not coming through? Just a bit of a new idea that needs to be toyed with a little bit? Okay, nothing in particular, or? Okay. Well, let's review a little bit. So the basic notion is that in order to generalize our notion of roots of equations, for example, a parabola that never manifestly accesses the horizontal axis, we need to expand our notion of real numbers into the notion of complex numbers. A complex number, complex means mixed, has a real part, which is x, and an imaginary part, which is y. Now, y itself is a real number. So the only place the I exists is right there. And whatever's next to the I, the coefficient of the I, is the imaginary part of the complex number. And then the part without an I is the real part. Again, the symbol most often that we define to express that is z, and that has nothing to do with the z direction. It's just we need a third symbol, and we use x and y, so we use z. Complex numbers can be plotted in the so-called complex plane. Real numbers exist on a number line, but complex numbers are two-dimensional, so they exist on a number plane. The imaginary part on the vertical and the real part on the horizontal. That's very good with that at this point. Now, very often it is convenient to use polar coordinates to express the location of the complex number. So in other words, just like when we were doing two-dimensional kinematics, let's say, we had the total velocity, we could give the x and the y components, or we could give the total velocity and the angle. Those were equivalent ways of encoding the same information. In the same way, complex numbers are encodable in terms of their distance from the origin, the radius, and the angle. The angle is always measured from plus x, counterclockwise rotation. So, x, the real part, is r cos theta. Y, the imaginary part, but which is itself a real number, is r sine theta, opposite side. So obviously, x squared plus y squared, which is the, what are we writing? Yeah. We're going to write this side squared plus this side squared is that side squared. So in other words, we're just doing what? Pythagorean here. So x squared plus y squared has got to be r squared, right? Now let me show you one other thing. You may or may not have ever actually seen or thought about this way. If we do this explicitly, x is r cos theta, right? And y is r sine theta, right? If we factor the r squared out of that, we've got r squared times cos squared theta plus sine squared theta. What's sine squared plus cos squared? 1. Why? It's just a manifestation of the Pythagorean theorem. Think about it this way. So we have the hypotenuse, we have the opposite side, and we have the adjacent side, right? So adjacent side over hypotenuse is cos theta plus opposite side over hypotenuse is sine theta. So since it's a right triangle, adjacent squared plus opposite squared must be hypotenuse squared. So this is just good. Now, the next thing that I want to introduce is an operation that we perform frequently, which is very useful. It's called complex conjugation. Have you heard of complex conjugation? So yeah, no. Complex conjugation is an operation. The operation is defined as follows, and we'll see after the fact here why it's a useful thing to sometimes do. Let me just define the operation. The operation is defined as follows. Turn all the i's into negative i's. So anywhere you see an I, replace it with a negative I. That's called complex conjugation. And why would that be a useful thing to do? So we have our normal definition of a complex number, right? Z is x plus iy. The complex conjugate is denoted as Z star. So if Z is x plus iy, what would Z star be?
X minus I.
That's it. Can everybody do that? Simple enough? Sort of a definition. But why is that useful? Well, it's useful for several reasons. But the point is this. ZZ star is equal to, well, let's multiply it out. ZZ star is equal to, well, what is Z? X plus iy in general. And then what is Z star? X minus iy. Now let's just expand this thing out. Just follow our noses. Let's multiply the thing out. We've got two terms in each expression, so altogether we should have 4 terms, right? We need every possible combination. So this times this is what? X squared. This times this is what?
Negative X IY.
Exactly. Now, this times this is what? Yeah. And then this times that is what?
Negative Y squared.
Yeah. Everyone look at it a little harder. We've heard the right answer now. This term times that term. Keep track of everything, okay? We've got plus times minus, that's minus. We've got I times I, what's that? Yeah, so two minuses becomes a plus, and then we've got y times y. So altogether, it's plus y squared. Let's do it out.
So because both the i's are actually negative. Right? So it's not like multiplying xy times xy. It's different.
Well, let's write it in a few steps. Let's write this as minus I squared times y squared. Do you agree with that? But then the I squared itself is negative. So altogether, plus y squared. Now, any simplifications? Yeah. Those are the same as each other except opposite in sign, right? So those cancel. So ZZ star looks to me like it's x squared plus y squared, which is otherwise known as what? Yeah. Exactly. So what we say is this. In words, a complex number times its own complex conjugate is the magnitude squared of the complex number. The magnitude of the complex number is its radius. The angle is what we'll call the phase. So in the complex plane, we have the two-dimensional plane. It's not a number line, it's a two-dimensional number line. Any point in the plane has a real part and an imaginary part. But we can also think of it as a modulus and a phase. There's some new vocabulary. Or we can think of it as a magnitude and a phase. Phase is the name for angle, basically. Very often, we want to get the radius. The simplest way to get the radius is to multiply the number times its complex conjugate. Another thing to notice here is that it's a real number. A real number. Z is complex. It may be real, it may be imaginary. In general, it's both. Part real, part imaginary. But ZZ star is real. So that's why the complex conjugate operation is important. It allows us to find the magnitude of a complex number. It allows us to write down something that we know for sure is real. It's always going to be real because the complex part cancels the way those cross terms cancel. The plus IY, obviously. The plus IXY minus IXY. At the very end of the day, last time, I wrote down something very mysterious that I said would probably look wildly mysterious to you at this point. But before the semester was done, would be something that you understood in and out, you know where it comes from, you know why it is. This is, if you ask professional mathematicians often what their favorite equation is, you can try Googling it, say favorite math equation or something. You'll come up very often with that equation. You'll see the name Euler, Leonard Euler, associated with it. It's a manifestation of this thing. It's a very beautiful equation. It's got kind of all of our favorite things in it. It's got this beautiful irrational number E, and we still don't know why E is E per se. Let me tell you, this is getting close to us understanding why. Before the semester's over, we'll know why E is E, what's so great about it. It's got pi, our other favorite irrational number. It's got I, the imaginary number. It's got a number raised to an imaginary power. You may not even have known that was possible, but it certainly is possible. And then it's got -1 in it, of all things.
So that C is an imaginary power? Is that what that is?
Oh, that's an I, sorry.
Oh.
I just got really excited with the tail of my eye. What's that?
Yeah, when it's negative, so that it makes it positive. Their eye.
I'm not sure I understand the question.
The eyes are negative numbers, right?
No, they're not negative, they're imaginary. I squared is negative.
So say we just take out the pi and have it squared to an imaginary number, does that make the number that's being squared by imaginary, or does that just mean that's a real number just to the power of imaginary?
This is a real number to an imaginary power, and in general, it's complex. There's some cases where it's pure real, there's some places where it's pure imaginary. For the particular value of the angle pi in radians, it turns out to be pure real. We're going to have to tinker with this a little bit, so let me show you the other thing. And again, we're going to use this a little bit and get comfortable with it, at least comfortable with the use of it, and you'll have to take it on faith that I mean this literally. But before the semester's done, I'm going to try to take some of these little loans I took out of faith and pay them back. So we're going to write that as r cos theta plus I r sine theta. R cos theta is just x in that way that we've thought about it before, right? And r sine theta, that's previously what we called y. Now, what is not obvious at all is that e to the I theta is really cos theta plus I sine theta. That's not obvious at all, at least not with the tools that we've got built up to this point, but it is nevertheless true. Let's tinker around a little bit more. Let me real briefly convince you that this is just a specialization of this. What's cosine pi? Working in radians. Yeah, how many degrees is pi?
Oh, that's negative 1.
Yeah, 180 degrees. So cosine has gone to -1. Right? What's sine of 180? 0. So if we put in pi, this is 0. This is -1. And we did, let's see, if we're comparing this to that, we chose a value of r, which was what? No.
No.
Do you see the number sitting there in front?
Oh, sorry.
No, the number sitting in front of me.
One.
Yeah, everyone sees the 1 sitting there, right? Right there? Everyone sees it? Right there. So this to that was that is a specialization of this with r equals 1 and theta equals pi. And sure enough, if we plug that into this formula, we get negative 1 here and 0 there. So that at least does match. Let's write this down. It's very, very important. If I wanted to solve for cosine theta, how might I do that?
Just subtract pi sine theta.
Okay, that's a good answer. Let me be more specific with my question. What if I wanted to solve for cos theta and sine theta independently from each other? So my equation for cos theta should not refer to sine, and my equation for sine should not refer to cos. What about that? What if we took the complex conjugate of both sides of that equation? What would the complex conjugate of that be? Well, what's our rule for complex conjugates?
Is it for both sides or just one?
You know, if we do it to one side, we better do it to the other. So we want it to still be an equation. What's the rule for complex conjugates? Turn all your eyes into minus i's. Okay, so what would the complex conjugate of that be?
E sine theta.
Okay, good. What's the complex conjugate of cos theta? Just cos theta. It doesn't have any i's, so it gets to stay the same. What's the complex conjugate of I sine theta? Now, we're pulling a little bit of a dirty trick here. The dirty trick is, I want to solve for two things, right? Cos theta and sine theta. If I want to solve for two things, how many equations do I need? Two. How many equations do I have? Two. How many equations is that?
Two equations that equal the same thing.
It's one complex equation. But in a complex equation, the real part on the left has to equal the real part on the right. And the imaginary part on the left has to equal the imaginary part on the right. Okay, so here's something important to learn. If you see an equation in complex numbers, it looks like one equation, but in some sense, how many pieces of information does it have? Two. So at the outset, I said we wanted to do something which Mike should have actually struck you as impossible. And you gave the right answer, was if you want to solve for cos theta, just take this thing to the other side. We're going to think about it on another level. I want this and this to be things that I can solve for. You say, you can't solve for two things with one equation. I say, well, you may not have noticed something. That's actually two equations. And the way that I'm going to leverage that freedom is writing it once in its normal form and once in its complex conjugate form. Now, with these somewhat more obviously dual independent equations, what can I do to those two equations together to get cos theta out, for example? Yeah. You know, I mean, I guess you could say I could solve for sine theta and plug it in and then solve for cos theta. A simpler way. Take these two equations and do what to them? Why? want to do something that would cause the sine thetas to cancel.
Or you would just put cos theta plus I sin theta equals cos theta minus I sin theta.
No, can't do that because these are not equal. Not divide, but what?
You can
Subtract. Yeah. Well, or add them more specifically. In this case, the minus sign's already sitting up front. If this is equal to that, and this is equal to that, then adding this to this should be the same as adding this to this, yeah. That should still result in equality. That should be equal. So if I add these two equations together, if I add these together, what am I going to get? Be careful, are these the same thing?
It'll be 0.
No.
So when we just
Yeah. There's no simplification. Now, if they were multiplied, their exponents would combine. If they were multiplied, that would be 1. E to the 0. They're not multiplied, it'd be that. So this plus this, there's no way to simplify that further in this context. Just have to write the two terms, add them. What's happening on the right-hand side? 2 cos theta. So cos theta is the sum of those things divided by 2. Okay. What would you suggest doing if I wanted to isolate the sine part instead of the cosine part?
just the sign, no imaginary
Ultimately, yes, but it can tag along for the time being. What would I do to those two equations if I wanted to get the sine part isolated while canceling the cos?
number. Would you subtract?
Subtract them instead of adding them. Does that work? So let's take the top one minus the bottom one. Take this minus this, and this minus this. Write down the two sides. Let's check ourselves in half a second. Oh, feels good. Is that what you got? Is that what you got? So let's write sine theta equals what? E to the I theta minus e to the minus I theta divided by 2I. Now, I don't very often ask you guys to memorize anything.
Oh, yeah.
But every so often, you just got to do it. This should go on your pillow. And these as well, unless you can immediately see them from this.
We need to start making order forms. Compelling basis.
Yeah, that's right. Yeah, it'll be like a letter jacket. You can have patches.
We use it on the test.
Or even I'll put your quote. I don't always ask y'all to remember things.
But you better.
But you need.
There are a few things you've got to know.
Put that on the next physics sheet.
This you've got to know. This is called the Euler formula. And these are just the inversions of that formula. These you should be able to get immediately by looking at that. Let me show you something slightly more general. Slightly. Maybe. Z is x plus iy, right? Z star, and just to throw something else in here, you'll see sometimes. You'll sometimes see a bar instead of a star. They mean the same thing. They mean complex conjugate. So Z star or Z bar is x minus iy. So this thing x is the real part of Z, yes. This thing y, not iy, just the y, which itself is real, is the imaginary part of Z. Let's follow the same logic we did over there. How would you solve for x? Yeah, yeah. So x would be Z plus Z bar divided by 2, which is the real part of Z. You see how this is including what we did over there for cos? Cos theta is the real part of e to the I theta. The imaginary part of Z is what? Otherwise known as y. It would be what? Minus Z bar divided by 2. That's right. Yeah. So Z bar does what? It turns the i's into minus i's. So if you add, the I parts cancel, but you got double the real parts. You got to divide by 2. If you subtract, the real parts cancel, but you got double the imaginary part. You have 2i. So you've got to divide the 2i. It's real clear to everybody that this and that are the same as those second equations over there. Well, now, what we're going to want to practice in lab this week, and on this week's lab homework, is going to be writing complex numbers in different ways. So we want to be able to convert freely between the RE to the I theta form and the x plus iy form. Now let me warn you about one thing. You might suspect it from our example, but I haven't told you yet, and you don't understand it well enough yet to definitely know that it's obviously true, that it is true. That angle theta had better be expressed in, what do you think? Radians. That's not optional. Now, if you're taking cosine of an angle or sine of an angle, you can express the angle in radians or degrees as you like. Just tell your calculator which one you're putting in, right? In this case, we are literally raising to a power. It is absolute, that equation does not make sense in anything other than radians. Now, let's do a couple practice examples, then I'll throw a curveball or two at you. So let's take let's take 5 minus 2i and convert it into the x plus iy form. So, I'm sorry, it's in the x plus iy form. Let's convert it to the r e to the I theta. So from this, let's read off. From this, let's read off. What is x? 5. It's the number with no i's. What is y? Careful. -2. So, if we were to graph that, it would be right there. Yeah, okay. So, the radius r, what would I write down to solve for r? Exactly. So let's do square root of 5 squared plus 2 squared. And we've just observed the squaring a negative is going to give us a positive. So 25 plus 4, square root, 5.5. Now, this is the angle theta that I want to solve for, right? But I'm going to get myself in trouble if I try to use arctangent without paying attention. Because tangent does not repeat, tangent repeats itself every pi, every 180 degrees. So there's always multiple answers to these inverse trig functions. And it may not give you the answer that's in the quadrant that you expect. So the safest way to do it, always, is just to define some other angle yourself, which is acute. So if you define an angle that's an acute angle within the 0 to 90 degree framework, then you'll be guaranteed that your sines are positive and your cosines are positive, and there's no place to make a sign mistake. So let's write alpha is equal to inverse tangent. What's the opposite side relative to alpha?
Y.
What number? Careful. We're treating this just as a triangle with absolute value side lengths. So what's the length of the side of the triangle opposite to alpha? 2. What's the length of the side of the triangle adjacent to alpha? 5. So looking at the graph there, 25 degrees. Both are just fine. Just be careful which one you've drawn, and then add, of course, add relative to your 360 appropriately relative to which one you've drawn. So I think the question raised was, why did you do this triangle instead of that triangle? It doesn't matter. They're both acute angles. Neither one will give you a mistake. If you wanted to define that, maybe call it beta. We could have said beta is tan inverse of what? What's the opposite side relative to beta? 5. So that works just fine. And then to get theta, we would add 270 to beta, or we would take alpha away from 360. Both just fine. So alpha, what do we get?
21.8.
Sounds good. Now, do we really want this in degrees at the end of the day? No, because if we're going to write it in RE to the I theta form, do we actually have a choice? It's got to be radians. So, two things we can do. two things we can do. We can put our calculator into radians mode and take the inverse tangent in radians mode. Or maybe the simpler thing to do is just leave your calculator in degrees mode. And then once you get this angle in degrees, multiply by what factor? Now, don't ever, very often, ask you to memorize it. If you forget this, the safest thing to do is to go back and figure it out. The safest, if you've forgotten something, the safest thing to do is figure it out. Memory plays horrible tricks on it. Theta is a part of 360 degrees, the same as theta radians is a part of 2 pi. So we want theta radians is equal to theta degrees times 2 pi over 360. Or, people usually write it as pi over 180. If you want a mnemonic for whether it's pi over 180 or 180 over pi, pi is more radians-like, right? So if you're going 2 radians from degrees, it's pi over 180. 180 is more degrees-like. If you're going 2 degrees from radians, it's 180 over pi. But if you get confused and you're not sure, don't sit there spinning your memory. Figure it out. It just takes half a second to figure it out. Okay, so 21.8, we want to convert that to rads. So is it pi over 180 or 180 over pi? Okay, so what's that in radians?
0.38.
0.38. Go ahead and give me one more digit there.
0.5.
Okay, perfect. Now, the angle that we want is theta all the way around. So the simplest thing to do relative to the 0.381 would be do what? I don't want this angle. I want its complement. Subtract that from 2.2 pi. And we've written the full circle as 2 pi, of course, because this number's already in radians. So what's our number on that? Great. So this number, as strange as it looks, is literally equal to 5.38 times e to the I. 5. Now, if you want to go the other way is maybe easier. The other ways may be easier. So given z is 4e to the 7i. That's a bit weird, but that's okay. It actually does more than a full map. It's not complicated. I want to put it in x plus iy form. Well, from this I can read off, right? From this, I can read off r and theta. What's R? 4. What's theta?
7.
Perfect. Now careful, that 7 is in radians. So if I want x, what should I write x as in terms of r and theta? Always let the picture guide you. Yeah. R cos theta. So 4 cos. Now, pay attention to which mode your calculator's in. If you're going to put the 4 straight into the parentheses, make sure your calculator's in radians mode. If your calculator's in degrees mode, then you could say, sorry, the 7, not 4. You could say 7 times, if we want to go from rads to degrees, is it pi over 180 or 180 over pi? 180 over pi. So that's what I would enter in my calculator if I was in degrees mode. Don't be confused about that. Circle degrees, 7 itself. And for y, what would I write? It's the same thing except with sign. Okay, so what did the top one turn out to be?
If it's in rating mode, we can just pop it to 7.
If it's in radio mode, just put in 7. I would suggest you do it both ways, just to get real comfortable with it. Make sure the calculator's behaving the way that you believe it ought to. Or make sure that what you believe it ought to matches what it's doing.
I got 3.01.
Okay, sounds right. And for this one? So the right answer now, at the end of the day, would be equals x plus I y. Now, I just want to show you one more thing real quick to make sure you're ready for the lab this week. This is the curveball I was talking about. We'll just look at it real quickly. What if we did something like 3i, 2i over 4 minus 3i? I want to read off x and y. Can you tell what x is? Nope. Nope. It's just not real easy to see in that form, right? Does it look like it's in the x plus I y? What we're going to do, this is the curveball. So a bit of a dirty trick, but we need to know how to do it. The thing that makes this a weirdo case is that it's got the complex numbers down in the denominator. Generally speaking, we don't like complex numbers down in our denominator. But there's something I can do that's guaranteed to make sure that the result is real. Multiply a complex number times its complex conjugate. So if down here I multiply, what's the complex conjugate of 4 minus 3i?
4 plus 3.
4 plus 3i. Am I allowed to do that? Well, no, not unless I also multiply up here. 4 plus 3i. Now, as long as I do it top and bottom, it's legal. But by choosing to multiply the denominator by its complex conjugate, I'm guaranteed that what's left will be real. In fact, can you see immediately what this number is going to be? It's a real number, a single number.
2i over 4.
4 squared is
That's
16. This and that term will cancel. This term is 3 squared, which is 9. And so 16 plus 9 is. Now in the numerator, 4 times 2i is what? 8i. 3i times 2i is what? 6i squared, and I squared is negative 1, so negative 6. Now it's in the normal form. Now can you read off x? Not just negative 6 by itself. Good. Can you read off y? Not the I, the thing next to the I. 8 over 25. And now we can play the game as usual. Fun? It is close. And it may or may not be obvious yet, but it's ridiculously useful stuff. I know it seems like we're playing more games for the time being, but this is ridiculously useful stuff.
In what aspect?
Quantum mechanics, engineering, performing integrations, it's scattering, circuit analysis. It's just all over the place.
All over.
Yeah. Anything that's sinusoidal, anything that involves a transfer function, almost anything that involves solving differential equations, certainly anything in quantum mechanics. Yeah. It's all over the place.
Just for curiosity's sake, is it always going to be stuck in a 2-number line, or can you add another?
Yeah, you could do whatever you like. At this point, you know the rules on how to multiply the complex numbers. You know how to, if you've got terms, you know how to multiply them out, combine real parts, combine imaginary parts. At this point, all the basic rules should be there. I think we can pretty much do anything. You can generalize from here. Go strong. All right. I will see you back.
Then it will